Hello and welcome, everyone. My name is Dane Menke. I am the Digital Marketing Manager here at Regenesis and Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please try refreshing your browser. If that does not fix the issue, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we do not address your question within the time permitting, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's webinar will focus on optimizing remedial performance results for high mass petroleum plumes. With that, I'd like to introduce our presenters for today. We are pleased to have with us Rick McGregor, President of InSitu Remediation Services Limited. Rick McGregor has over 30 years experience in groundwater and soil assessment and remediation, has worked in over 30 countries, and has authored numerous papers on groundwater assessment and remediation. He holds a Master of Science degree from the University of Waterloo in hydrogeology and geochemistry, and is a certified groundwater professional in Canada and the United States. We're also pleased to have with us today Todd Harrington, Director of Product Management for Regenesis. Todd Harrington has 25 years experience in the remediation industry and an in-depth understanding of the complexities of in-situ remediation, having evaluated or implemented mechanical, biological, and non-biological in-situ remedial technologies at over 1,000 sites. He graduated from the University of Cincinnati with an MS in environmental engineering. All right, that concludes our introduction. So now I will hand things over to Rick McGregor to get us started.
Thank you, Dane, and thank you for the invitation to give this presentation. So today, as Dane mentioned, I'll be talking about a treatment of a groundwater plume with high BTEX and petroleum hydrocarbons within it, using a variety of methods, and how we finished off the plume. I'd like to acknowledge my co-authors, Ben Galbraith, Melina Sebra, and Matt Hint, who have helped with the study as well as helped with the presentation. So we'll start with a new agenda. So we're going to give a very brief overview of the fate transport of LNAPL and BTEX, which is of concern at this site, and then we'll introduce the site and go through the brief history of the remedial technologies that have been used at the site. You'll see us and others have used about 8 or 9 different technologies at the site to address the LNAPL and dissolved phase plume. We'll go through the objectives of the study we'll be talking about today, and then we'll look at the methodology, and then followed by the results and discussion, and then a brief summary, and then I'll switch over to Todd, and then afterwards we'll have a Q&A session. So a quick overview of LNAPL and how it forms plumes in the ground. Most of you have seen this, and I refer anybody to the ITRC documents. They provide an excellent overview of how NAPL and plumes form. And the reason we're going to do this, just make sure you always have to keep in your mind when it comes to remediation that it's usually a very complex, and we're dealing with multiple phases. In case of a release in the vadose zone, we're looking at vapor as well as LNAPL forming on the water table if there's enough LNAPL released. And then we're looking at the absorb and dissolve phase. Today we'll look at all 4 briefly at this site and how they were handled, but mostly focus on the dissolve phase. Things we have to think about when we're designing remedial programs, of course, are dispersion, chemical degradation, biological degradation, and volatilization if we have a lot of vadose zone to consider. One of the things that you really need to understand when it comes to LNAPL and BTEX hydrocarbon plumes is the release of the LNAPL to the groundwater. This is just once again from the ITRC and just shows how LNAPL, when it's released, how it accumulates at the water table and how you can have 3 different phases present. So if we go left to right here, basically you're having the LNAPL released, and then you're seeing the 3 phases form: the absorb, the LNAPL itself, and then the water in the air. So as it goes down, you get saturation of the soil with the LNAPL, and if you have enough, you get it accumulating on the water table. Now, over time, the LNAPL thickness will vary with the fluctuating water table, and what you get is, most people call it a smear zone forming. This can be very problematic from a remediation point of view, especially for deep remediation. So the other thing is how do we understand what we see in wells? Usually LNAPL is detected in wells. There are high resolution techniques out there like the UVOS and the technologies out there that can detect NAPL in the soil in the vadose zone, but usually NAPL is usually detected within presence in wells. And how do you interpret that presence in wells with what you have to remediate? So you have to look at the different stages. We're not going to get into this, but it's something that when it comes to remediation, a lot of people forget some of these basic steps and understanding the conceptual model in the flow and transfer to NAPL and the associated sulfate plumes, as well as the vadose zone plumes. So this is just a reminder, and once again, I strongly recommend you look at documents like the ITRC documents. So we'll get right into the site. So it's an active gas station with multiple underground storage tanks. It has been in operation for over 30 years. And interestingly, the owner of the station does a leak test every so often. And the leak tests have always come back, quote unquote, passed, suggesting there's no leakage of the tanks. Unfortunately, somewhere along the line, the data in the LNAPL in the ground doesn't agree with the results of the leak testing. So it's once again a little bit of a warning that leak testing do have I call it a detection limit, like most things. And that detection limit allows for a certain percentage of gasoline or diesel or hydrocarbons to be released without the system actually triggering any warning. So you need to be careful about that. And like most data, just take it with a grain of salt and do the thing. So the site itself is a 70-foot thick vadose zone consisting of sand to a very dense sand as you go down. Now it is heterogenetic with layers of higher hydraulic conductivity in that. So our hydraulic conductivity varies from about 110 to -3 to 9 times 10 to -4. So it's very quote unquote homogeneous. However, these are bulk hydraulic conductivities and it doesn't really take into account finer or coarser grain or higher and lower conductivity sand seams or silt seams that may exist. It is a glacial fluvial deposit, so and what we would call an esker. So it is fairly permeable and groundwater flows at a moderate velocity of about 30 feet per year. It is unconfined. As you would expect in a hydrocarbon plume, it is iron sulfate reducing, and this aquifer is buffered quite well with carbonates. Our chemistry, this sums it up now. This is the worst case chemistry for the hydrocarbons. And as you can guess, they're basically samples taken almost immediately down gradient of NAPL. So we have BTEX at about 122 micrograms per liter with the gas range 154 micrograms per liter, diesel range about 3,700 micrograms per liter. And of course, we have some of the pHs associated with this. We had a fair bit of naphthalene present. We'll talk about that a bit later as the University of Toronto PhD student there. I did a lot of research on looking at the naphthalene mobility at this site. Inorganics, these are within the core of the plume itself. So really we have no electron acceptors in the core, which you would expect. We have very low iron in our core, which is a bit of a surprise, but this is a nice clean sand with very few iron deposits or iron coatings on the soil itself. So that's not surprising, but you'll see we do have some manganese hanging around. Prior to remediation, we did have some methane occurring in the groundwater up to 1 milligram per liter, so fairly good concentrations. And as I said before, our groundwater is well buffered at about 6.8 to 7.2, which you would expect for carbonate buffered aquifers. So the site history itself is a bit interesting. Prior to us being involved, there was a pump and treat system put in. Pump and treat system, not much knowledge is known about it. However, we do know it enlarged the smear zone significantly near where the system was. We ended up with, we know groundwater fluctuates about a meter over the 10 years we've been working on site. And yes, you heard that right, 10 years. But the smear zone near where the pump and treat wells were about almost 3 to 4 meters. So they were doing some significant pumping, but they were smearing a lot of product. We're not quite sure what the objective was because it really does not appear to have been effective in containing the plume, and it sure wasn't effective in reducing much mass of the plume. So as we became more involved, there was an MPE system, multi-phase system put in, and it removed about 9,500 kilograms of LNAPL. It did a fairly good job, but it got to a point of diminishing returns. So The next technology brought in was an air sparge SVE. Remember, we had 70 feet of vadose zone here, and most of that vadose zone was impacted underneath the tank. So we had significant mass within the vadose zone, as well as on the water table itself. So over that operation of about 8 years, they pulled out about 10,500 kilograms of hydrocarbons out of it. At the end of that, we had removed all the NAPL, except for one small area that had a little bit of NAPL. Access was a bit difficult for the SVE system. So we decided to do a surfactant push-pull flushing test at that area, which was to address the NAPL in the 1 or 2 wells that still had NAPL. And that was very successful in doing that. So basically, we injected a surfactant solution down the wells and then waited about 24 to 48 hours, and we pulled that surfactant enhanced groundwater back and pumped it to the surface. After that was done, the NAPL was removed. So we just didn't willy-nilly decide on what technologies to use and when to change them. We actually used this as an old concept put up by the EPA back, I think, probably in the 90s, where we looked at the cost of contaminant removed on a mass basis and looked at it over time. And what you'll see here is this is a kind of a classic graph. Is initially your cost is very expensive, and then as you get more and more efficient and remove more mass, your cost per unit mass decreases until it bottoms out. And then it usually starts to increase as your diminishing returns happen. And so usually we want to change the technologies or reevaluate or optimize the technologies once we start to see that upward curve. So this is kind of what we use as a basis for our decision making at the site. Here's a very schematic cartoon of the source area with the 2 associated plumes. I just did the BTEX plume, the LNAPL plume. The overall BTEX plume was about 400 feet long, which is typical for most large BTEX plumes. And then the LNAPL plume itself was about 150 feet, which is a fairly significant LNAPL plume. It varied from about 5 feet in the core to down to a sheen, but it was fairly large LNAPL plume. This is prior to the MPE system being in, so post pump and treat, but pre-MPE and SVE and air sparge. Following the air sparging and SVE and MPE, what we were left with was this basically a small pool of LNAPL around 2 wells, kind of downgrading at the tip of the LNAPL plume. So that was what was addressed with the surfactant flushing program, and it was removed successfully. So what we're left with was a large BTEX plume, about 400 feet long. So that was decided at this point we would go to passive technologies. So once again, we're looking at 3 different passive technologies. We used enhanced aerobic bio, which consists of using the Waterloo emitters, which release oxygen 24 hours a day, 365 days a year, just basically through diffusion, through a tube that's in the ground, and then that diffuses, the oxygen in that tube diffuses into the groundwater and basically creates oxygenated water in that area. It's very passive, but we used it as a plume containment technology. So basically, if you want to think of it as a PRB composed of Waterloo emitters. In areas of high dissolved phase, we decided to target those to try to knock down the mass of the hydrocarbons using chemical oxidation. In this case, we used activated persulfate or catalyzed persulfate in some cases. We use both. And what we want to do here is reduce the mass within the smear zone as well as reduce the mass within the plume. Following that, we followed it up with the PetroFix colloidal activated carbon technology, and that was to go after the same areas and basically remove the petroleum hydrocarbon mass within the plume, as well as address any potential back and matrix diffusion reactions that could happen down the road. So our objectives for the site were, first is, let's evaluate, make sure the PetroFix can work on the high mass flux areas of the plume, the BTEX, the gas, and the diesel plumes, as well as you look at the effectiveness of the PetroFix on back diffusion, matrix diffusion that we thought we may see over time because we did have some fine materials within the overall aquifer. And finally, we want to do, and mostly what this talk is about, is since we're dealing with a high mass flux BTEX and other component plumes in some of these areas, we wanted to look at what's the effects on the lifespan of the PetroFix, because PetroFix, as Todd will talk about later, is a activated carbon technology that has finite sorption sites. So you could technically overwhelm the carbon if you have too high mass flux on it over time. So we wanted to look at what happens if we enhance that. Now, PetroFix, as Todd will talk about, already comes as a mixture, or you can customize it yourself, of electron acceptors, but we wanted to enhance those and add more electron acceptors to see if we can reduce the mass flux onto the carbon, and secondly, to see if we could speed up the kinetics of the reactions occurring right at the start, as most clients really want to see results very quickly. So we were looking at that to see if we could do that. So we divide the site up into 4 nil test areas. Each one's about 1,000 square feet in area, and we're targeting the water table and the smear zone. So area 1 was straight old PetroFix that Regenesis supplies with its enhancement. In this case, we used a sulfate nitrate enhancement electron acceptors. Area 2 was PetroFix with ORC added, oxygen releasing compound. Third area was PetroFix with a sulfate salt added to it, and fourth area was PetroFix with a nitrate salt added to it. So we're looking at the 3 main electron acceptors and seeing if we added more of those electron acceptors than what came with the PetroFix, could we actually increase the kinetics of the reaction and also make the lifespan of the PetroFix longer. This is a classic diagram, most of the thing, but one of the things we're obviously trying to do is enhance the biodegradation of the hydrocarbons in BTEX in particular. So most hydrocarbon plumes, a lot of them have these zones in it. So outside with not affected tend to be aerobic, maybe not, depending on the depth of the plume, as well as then as you go through these classic stages of nitrate, iron, magnesium reduction, then you get in sulfate reduction and then methylogenesis. Generally speaking, the reactions or the degradation of the hydrocarbons rate or the kinetics increases as it becomes more aerobic. So as you go left to right, those kinetics with the degradation of hydrocarbons speeds up. So in the ideal world, you would oxygenate most of your hydrocarbon plumes, and that would be great. Unfortunately, oxygen has a solubility limit, and it is consumed by a lot of other electron donors, so oxygen, and it tends to be more expensive on a per mass basis. So there are different methods to go at it. This table is from Dr. Jim Barca, formerly of the University of Waterloo, and a bunch of his grad students. It's a nice summary of, and it's a bit out of date, but it's not too bad out of date, of basically looking at the main processes, degradation processes along the top, and looking at various hydrocarbons and saying, is there peer review papers that show these reactions happen? So it's a nice little summary. Obviously, this changes monthly based on who's out there, and the question marks are, somebody's kind of showing it's happening, somebody says it hasn't, so there's a bit of a debate. The capital yes is for sure, there's no doubt that happens. The smaller yes suggests it's happening, and it's likely yet. But anyway, this is a nice little chart that I like it. It's a nice little guideline to what's going on. So here's the thing of the 4 test areas. You'll see test area 1, where the PetroFix was used, was right near the source, but the LNAPL plume extended down to test area 2 and just stopped upgrading of test area 3. So all 3 of those areas had very high BTEX mass fluxes through it. In test area 4, there was a seam of high conductivity, and it also had a fairly high flux. So we picked these 4 test areas within the core of the plume to do the test. So as I said, the first one was done with PetroFix with the Regenesis supplied nitrate sulfate electron acceptors. The PetroFix was injected using direct push technology. Area 2, the PetroFix was enhanced with oxygen releasing compound, and it was once again injected with direct push technology. Area 3 was with 2 forms of sulfate, calcium and sodium sulfate. It was injected in injection wells. I'll be honest, I was sleeping on this day when I did this design, and we originally went out there with calcium sulfate in the form of gypsum. One of the things is the calcium, the divalent cations can actually, I won't say negatively react with the carrier fluid of the PetroFix, but it breaks it down. So you don't get the transport that you would if you're just using a monovalent cation such as sodium. So we originally started with calcium, and unfortunately we're getting some back pressure in the injection wells, and we switched over to sodium, and that solved the problem. So it's something you need to consider when you're doing design. A lot of people like to use gypsum, but it will potentially, depending on what use you have, negatively impact your distribution of your PetroFix. Finally, we used a PetroFix with a nitrate salt, and it was injected using a combination of injection wells and direct push technology. You're probably asking why we used 2 different technologies. It's 70 feet deep We had to get it to about 80 feet, and the dense sand was actually, in some cases, impossible for us to get that depth. So a lot of injection points we had to pre-drill, backfill with a bentonite mixture, and then go back and re-inject. So in some areas, we just decided to put injection wells in. And in one area, we used injection wells on an angle. So that's kind of why we did it. So monitoring networks, we are looking at traditional monitoring wells as well as CMTs, which are a multi-level system that developed by University of Waterloo, give you excellent vertical delineation of plumes and monitoring. We obviously did the classic organic analysis of gas, diesel range, as well as BTEX. We did a range of inorganic chemistry as well as carbon-specific isotopes, as well as detailed microbiology, which will show some results. And we did obviously water levels and LNAPL presence. We also took cores of the soil in certain places to look at the modified total organic carbon. Basically, allow us to look at concentration of activated carbon before and after injections. We also looked at the FOC of the aquifer. That was kind of a before number. And then we looked at visual cores. Anybody who hasn't used PetroFix or its cousin PlumeStop, both of those are very black, and they cover the aquifer solids very well, and they're very black when you do the injection. So they're visually very easy to actually see if you've injected in the areas you want. So this is the results for area 1. So this is PetroFix with its comes off the shelf electron acceptors added to it. Here the groundwater is flowing left to right. Water table, we have what I call a treatment zone here. And you can see this is post-injection. This is, I just picked xylenes. This is a cross-section of the concentrations going into the treatment zone, and then within the treatment zone, down gradient treatment zone. As you can see, we had a plume about 1,000, maybe a little higher, coming into the treatment zone of xylenes. And then basically right within 30 centimeters to 50 centimeters of the up gradient portion of the treatment zone, xylene went below our guideline, which here was 5. Our treatment guideline was 5 micrograms per liter. But by the time we, you can see we had some trace concentrations, but by the time we got out, we're well within our treatment area. And by the time we got down gradient after a certain period, it basically our concentrations were all at detection limits. So this showed this far. So we've seen the similar results for all the BTEX compounds as well as the gasoline range. Diesel took a little longer to treat, as you would expect. When we look at treatment with time, you can see I put the different technologies that have been used on the site following the removal of the LNAPL. The air sparge SVE was put into about 17 months into the operation. And what we were seeing was a spike or rebound, you can call it what you want, of the concentrations getting up to over 11,000 micrograms per liter BTEX. So that's when we implement the air sparge SVE, and we've seen a nice drop over time, but we kept seeing every time we turn off the system and let it sit for a bit, we would see rebound happening. The rebound was decreasing with time, but it wasn't decreasing fast enough. So that's when we hit it with the chemox, in this case activated persulfate, as well as catalyzed persulfate. And then we see a nice decrease, but once again, over a 3 or 4 month period, we've seen a rebound basically back up to actually concentrations greater. And that's when we decided to bring in the PetroFix. And we did the PetroFix, and over a 40-month period, we've seen the PetroFix basically take the concentration of BTEX down to below detection limits over the 40-month periods, and they've stayed there. We did see a little blip there. We think that was due to a very high water table at one time that might have picked up something in the vadose zone that hadn't been addressed. When we went in and did some bacteria or microorganism analysis, this is just a bubble plot showing various organisms that were detected. I'm not a microbiologist, so please don't grill me too much about this. But basically, there's 3 graphs here. The plot on the very left is pre-injection of the PetroFix, and then the other 2 are post-injection of 2 wells that were within or near the area. You can see that there's definitely a big change here. I won't get into the actual microorganisms themselves, but you see there's a really big change in the microorganisms that are present. And basically what we're seeing is a combination of nitrate reducing and sulfate reducing bacteria increasing percent-wise versus what were there before. So that's what we would expect. We're injecting a nitrate sulfate salts that are there to promote biodegradation by nitrate and sulfate. For area 2, which is with the PetroFix with oxygen releasing compound added, similar plot here. I picked dissolved oxygen because we were actually adding ORC. And what you see here is Oxygen coming into the treatment zone is pretty much near detection limit, except near the surface where we're getting oxygenated water through infiltration happening. But overall, you're seeing concentrations basically 3 milligrams per liter or less, and occasionally we see higher ones, and that might be residue from the air sparge system that was in there properly. But basically, we're seeing a very anaerobic plume coming into the treatment system. And then we see a big increase in oxygen, as you would expect, because we injected ORC. And then you're seeing downgrading, the oxygen decreasing a bit as it goes downgrading, but that's probably due to the biological reactions as well as reactions with other reduced species. Once again, this is just a plot showing treatment with time with the treatment technologies on there. Air sparge, once again, air sparge was good at an SVE. We're good at knocking down the concentrations from about 5,300 down to less than 1,000, but then we had a rebound back up to about 2,000. That's where we hit it with the catalyzed persulfate. And we've seen a decrease, about 50% decrease, but still then it bounced up similar to the area 1 where the chemox rebound was greater than it actually was initially. So that's when we went in with the PetroFix and ORC, and really a first sampling event after we hit the ORC was below detection limit, and it stayed at detection limit for the next basically 55 months. So that was great. The ORC looked like it responded very quickly, and it has maintained its non-detect for over 3 years now. Once again, we did similar type of microbiological analysis. So we have the pre-microorganisms on the left, and then once we inject it, we have the core of the plume, what I call post, and then the fridge of the plume on 2 different monitoring wells. And once again, you can see that the bacteria population community has vastly changed after the addition of the ORC. And so once again, I won't go into things, but basically what we're seeing is aerobic loving bacteria growth in the core of the plume where we added ORC. Once we get to area 3, this is where we added sulfate. So sulfate is a common additive for a lot of people because it adds the advantage of has a very high solubility. It's a slower reacting, and therefore it should last a lot longer than things like oxygen and nitrate within the ground. So the downside using sulfate is that it has limited compounds that will degrade or create conditions that will allow biodegradation, as well as it's a slower kinetic reaction than compared to nitrate or oxygen. So once again, we have the 3 technologies on here, and you can see same path. The air sparge knocked things down from about 15,000 down to about 3,000 micrograms per liter. Then we started to see a rebound again. So we hit it with chemox and it went down. But once again, we've seen that same type of rebound with the chemox that we've seen at the other 2 areas where it came back up to greater concentrations, not much, but basically same or greater concentrations than we've seen prior to the chemox. So in this case, we hit it with the PetroFix as well as the calcium/sodium sulfate. And within the first sampling pit, we've seen it almost go to detection limit. But over time, over the next 45 months, 3 to 4 years, we start to see it climb. Now it's leveled off to about 300. So we think that's a kinetic thing where the sulfate reaction is just taking longer. So where we're monitoring from, that reaction hasn't been able to go to completion. We see evidence of that down gradient now, where some of the down gradient wells are seeing drastic decreases in the BTEX. Once again, we did the same thing pre and post, and you can see the dramatic changes in the organisms, microorganisms within the groundwater, within the monitoring well, within the injection area. Here, we won't get into it, but the bacteria that are really the big green and yellow dots, those are bacteria that are very anaerobic, and which is what you would suggest with the sulfate happening. So not surprising we see these bacteria, but once again, this is very dramatic differences in the microbiology. In this area, we decided to do compound-specific isotope analysis to see if we could see any signature of the sulfate reduction happening. We knew we had bacteria there that was doing it, but we thought, well, maybe we can see if we can find that with the compound-specific isotope. So we analyzed carbon and hydrogen. And what we've seen here, especially the top 2 graphs, the red dots and the blue squares, the change in ratio basically between the hydrogen and carbon increases with time, especially in the short term, suggesting that we do have sulfate reduction occurring. You also see that with the black dots just over the short term, but then you see a rapid decrease in the ratio. with time. So if anybody, we can talk about that, but we won't get too much in detail about that today. But as you can also see on the right axis is as the concentration of sulfate decreases, we're seeing a decrease in concentration of sulfate as we go with time, which is what you expect with sulfate reduction happening. The last area we checked was the area that we injected PetroFix with nitrate salt. Once again, we have the air sparge coming down. We did not do chemical oxidation in this area. We have the air sparge coming down, and then once we've seen it start to rise again after we turned it off, that's when we injected the PetroFix in the nitrate salt. And once again, we've seen a little slower decrease with time in the concentration, and we've seen the nil bump about 108 months out, but then we've seen it decrease down to detection limits, and it's just slightly risen a bit over time as the nitrate has been consumed. So we're seeing a bit of rise, but once again, it's about 50 to 60 micrograms per liter, so nothing too significant right now. And once again, we did the microbiology analysis, and this is pre and post. Once again, you see a dramatic, well, not as dramatic, but a dramatic change in the microbiology community with the denitrifiers and the nitrate-related bacteria, obviously population growing relative to the sulfur reducers that were happening before. So in summary, we're talking about treatment efficiency. So what we did was look at 6 months post-injection of the PetroFix and its related electron acceptors and 36 months. So short-term versus moderate terms. So area 1, once again, is just PetroFix with its regular electron acceptors. So after 6 months, we've seen 94% removal of this is BTEX, of the BTEX. And after 36 months, we're basically below detection limit. So we're greater than 99.5% removal of the BTEX. Area 2, which has the ORC, within 6 months, we had removal down to detection limits, and that's been retained for 36 months. For the area where we added area 3, where we added sulfate, once again, you've seen the BTEX concentrations drop to about 94%, and then over 36 months, it's been about 95% over 36 months. Then finally, the nitrate, we've seen about 92% removal over the first 6 months, and then it's increased its removal rate to basically down detection limits with greater than 98%. So what's this telling us in a way of kinetics? And we did other calculations that we don't have time to get into today, but it basically suggests that the ORC with PetroFix was the fastest kinetics of all the different supplements we added, and it's maintained its removal or treatment efficiency over the 3 years. Actually, it's over 3 years now. The PetroFix and the sulfate enhancement, they basically have the same type of kinetics at the start, but the PetroFix off-the-shelf additives have actually had better removal over the long term than the sulfate. And once again, we think the sulfate is just a slower kinetics, and therefore, as you go probably down gradient in the sulfate continues to react with the bacteria, that you'll see higher reductions there. The nitrate was a quote unquote the slowest kinetic reacting test, but over time we've seen it did get down to detection limits. Now after 36 months we're starting to see it rebound a bit because the nitrate's not all gone there. Basically, and the next question is do we still see any evidence of any of the additives we added there? And basically the only ones we see evidence still of is sulfate, where we added more sulfate. In the PetroFix, where we added smaller amounts of sulfate, the sulfate is now depleted in that area. The graph on the right is from microbiology, and I find this a little bit interesting. It basically looks at the areas and how many microorganisms we were able to, or the lab was able to sequence out of the groundwater within each test area. And at first you see at the PetroFix area where we injected that, they were able to pick up about 430 different organisms in their sequencing, which by far was the most diverse microbiology or microorganism population of all 4 areas. I don't have on here the sulfate. The sulfate was similar to the nitrate. The second most was where we injected ORC with the PetroFix, where it had about 180 different microorganisms detected. And then finally, the nitrate sulfate, where about 100 to 120. And so this is not a bad, the number of different organisms isn't a bad thing. It just means that when we injected something, the organisms adapted, and the ones that flourished in that type of geochemical environment dominated and eased out the other ones that could not thrive in that. So once again, it shows that the bacteria were very quick at adapting to what was injected. So our findings, summary of our findings was the PetroFix could be injected effectively, and I don't show the cores here or the results from the cores, but if anybody wants to see them, we happily provide Regenesis with those and they can pass them on. But when we looked at the distribution, all 4 areas had very good distribution within the target injection zone. So it didn't really matter though. The direct push was no better distributed than the wells, but overall the injection was very good for either technology. As I said earlier, if you're using sulfate or nitrate and you're adding it yourself, then you need to be careful using divalent cation salts due to that potentially negative reaction with the carrier fluid of the colloidal activated carbon. All the mixtures modified the microorganism community in all 4 test areas and very significantly. So that was good. We've seen quick adaptation of the microorganisms and they seem to be sustained over time. Once again, probably most importantly, we had excellent treatment in all 4 areas over the short and moderate terms. We met the treatment objectives for the site in all 4 areas, and it's sustained itself over almost 3 to 4 years now. The populations, and this goes back to the 3rd point, basically reflect what we were injecting. So no surprise there, and that was good. Kinetic data, so I showed you some of the time things. Now we also went at mass and looked at mass degradation with time based on results. And it was pretty clear at the end of the day that ORC enhanced injection was the fastest of the 4 sites. That was followed by nitrate PetroFix by itself, where basically showed kind of the same rates. And then the sulfate was the slower one. That said, the sulfate one with enhanced sulfate still has sulfate present, so it might have a longer lifespan than the other 3 areas. And with that, I'll just thank the grad students and companies that helped us look at this site. University of Toronto, a PhD student up there, University of Waterloo had some students help us with some stuff, as well as Serum, which did a lot of the analysis and helped us do the interpretation. Orphan from the Isotope Tracer Technology Lab in Waterloo did a lot of the, well, he did all the compound-specific isotope analysis and helped us with the interpretation, as well as my employees. With that, I think I'll pass it over to Todd and let him talk more about PetroFix and its uses.
All right, thank you, Rick. That was a great talk. I always appreciate the work you do in the field, your curiosity, and how you bring a lot of that applied research and science to the market. I want to give some basics on PetroFix, and I'm going to focus on some things on PetroFix we don't normally focus on, primarily, how we pick the electron acceptor package and why. I'm actually going to get into a brief case study towards the end of the talk as well. But in terms of who Regenesis is, for those of you who may be new to us, we've been around since roughly 1994, and we're an advanced technology vendor for InSitu remediation. So we develop InSitu remediation technologies, all sorts of different kinds of those, as you can see here from this development chart over time, and even some have been obsoleted in gray. And they cover a bunch of different things: aerobic, anaerobic bio, InSitu chemical reduction, absorption for PFAS, things of that nature. But what is interesting to me in the last 11 years or so is the development of colloidal technologies. Colloidal technologies are very small. They allow us to put our technologies into the subsurface, using low pressure to get homogeneous distribution. And so we've developed about 6 or 7 of these over the past 11 years, used for a variety of different contaminants. Now today we're talking about PetroFix, but they can be used for absorption for PFAS, for CVOCs, and other types of contaminants. Now, what's special about a colloid is that it's stable when shipped, it's stable when mixed. And so when we dilute it, it's a material that has a low viscosity. It's easy to go into a well or down a rod. Now, in comparison, a destabilized microscale non-colloidal material like a powdered activated carbon will settle. And those materials, as I'm sure Rick would attest to, can be a little bit harder to get in the ground. You need higher pressure. So this colloidal homogeneous mixture of micron-sized particles allows us to go into the subsurface And I like to call it floor to ceiling coverage of an aquifer without really worrying about it fracking or high pressure moving out of the source area or into a corridor or well. Most other materials, even Rick mentioned oxygen release compound advanced, that takes a little pressure. That tends to have sometimes a bit of fractured flow depending on how you put it in, but it helps us overcome some of the challenges with fracture, gaps between fractures, possibly going to utility corridors. These are some of the big benefits of all those 7 or 8 colloidal technologies, including PetroFix. So ships at the site, it's plus 30% by weight colloidal activated carbon. The package that Rick mentioned is a sulfate nitrate combination that comes in separate buckets and is put into the mix tank before it goes down the rod or into the well. And the reason we do that is I think Rick did a really nice job on that. It's really just promoting biodegradation. To specifically say what it does is that the PetroFix, Rick mentioned it turns the soils black. The PetroFix itself doesn't clog an aquifer. What it does is it coats the aquifer in a very small, thin layer. The sand particle image on the left, taken with a microscope, shows the PetroFix particles on a sand that are adhered to that sand. So once it's adhered to it, it forms a thin adsorption layer. Contaminants go on that, and when you add the electron acceptors, biofilms grow. Those biofilms are in close contact with the carbon, and you get the biodegradation and regeneration of the site. So, there's a lot of electron acceptors to pick from, but when we had to decide, ease of application, I think really stood out for us was one, and the idea of syntropy. So, being able to mix, say, we use soluble ammonium sulfate and sodium nitrate. Those are both monovalent cations, and they're electron acceptor salts that we use. And they dissolve and can be co-mixed with the PetroFix, and they co-inject with it. So we get, perfect contact. And as Rick said, nitrate is very good for, say, benzene. It's got a broader range of treatment capabilities. Sulfate is the slowest, but it's still versatile. I would say if we had a soluble form of oxygen, we'd love to do that, but that is hard for most people. We don't have that. We do have oxygen release compound advanced. That can be difficult to co-inject. It takes a little bit of skill to do that, and generally we avoid it. Somebody like Rick can do that, but we prefer to do a nitrate sulfate combo, a standard package. And the other thing that it does, there's been a lot of research over the last 10 years or so, some papers actually back about 20 years ago now, that when you use combinations of electron acceptors, and I'm going to go on a limb, watching Rick's presentation, it seems that in the long run, the PetroFix nitrate sulfate package is holding its own at 3 years. One of the neat things when you do that is that what happens with biodegradation is things tend to stall out when you run out of the electron acceptors. And one of those things that stalls is fermentation. Fermentation and methanogenesis actually are some of the heavy lifters for bioremediation, but there's waste that accumulates, and that waste is in the form of, say, hydrogen and acetate. When you add electron acceptors like nitrate sulfate, what they do is it kickstarts it forms a biomass, and what happens is these wastes start to get removed out of the system, which kickstarts syntrops. Now, syntrops are a type of fermentative bacteria that are dependent on other bacteria to live and thrive. And so when you have these other nitrate reducers and sulfate reducers going, you start to get this engine rolling, and then methanogens kick in. They start to convert hydrogen or acetate into other byproducts such as water and methane, or carbon dioxide and methane. And the point being is that this is a phenomenon that really allows contaminants to be biodegraded even after the presence of nitrate and sulfate is no longer detected. Now, theoretically, when we add sulfate nitrate, as Rick showed, it comes up and it goes down and it goes away. What you would expect to see is biomass go up, maybe go back to background over time, or maybe stabilize. He was showing total microbial populations. This is a site in Indiana where we saw, similar curves to what Rick was showing. We saw nitrate or sulfate go up and it came down. This little blip was actually, there was an injection adjacent, and they started to get some bleed in of nitrate and sulfate. But what we did see in terms of biomass growth, now we did do some advanced diagnostics like Rick was showing from a company called Microbial Insights, and specifically they have a tool called the QuantaRay Petro. And we took that, and then I boiled it down and just took 3 of the targets out there. I'm looking at total U bacteria, sulfate reducing bacteria, and PM1 bacteria responsible for M2B degradation. Notice that the total U bacteria, which is a total estimate of all the populations of the bacteria, it doesn't distinguish between sulfate reducers, fermenters, fermenting bacteria, sulfate reducers, et cetera, but it goes up even after the electron acceptors were depleted in November. They continue to go up. And so if we look at that, we see methane generation continue. We don't have carbon dioxide data, but you would see higher levels of that over time, roughly about 2 times over baseline. And so we know over the long term that we get some of this syntropic fermentation, methanogenesis cycle. So I think that's a couple of the neat things on using nitrate sulfate together, and that can be seen more in a tech bulletin that we have. It can be found on our website. If you have time, this QR code is for Microbial Insights, company that we like to use in the United States. If you find it necessary for regulatory support to show the occurrence of bio through a specific gene target. So you saw Rick in his case studies, his research have sites that use air sparging, ISCO, and ISCO in particular. Typically, people will transition from physical or ISCO into something like a PetroFix, but what we're finding is with his site with high mass, it might actually be possible at times to rely on PetroFix instead of an ISCO application to handle what you need to handle. Now, that could be you have high concentrations and maybe you don't have to get down to 1 part per billion, but it could be a risk-based type of closure, like something that I'm going to show you next on a site. So we have a site here that was done on the East Coast. This was a site historically utilized as a retail service station. The reason I picked this site is it's fairly recent. We actually just published this a couple months ago. It has high mass and it has an integrated use, actually in this case with an ISCO product that we have called Regenesis. The site itself, this is the former gas station building. We're down to the pad, and what you see here is the former tank basins here in green. So we're looking across from this lower angle over here off in this direction and across this towards the equipment being used to do some of the injections. The fueling pads were right here, and there was a lot of free product, a lot of contamination, very, very high that was in here. I believe if you add it together, it was probably above 50 milligrams per liter. The goal was to eliminate measurable LNAPL in this well MW11 right here, to get benzene below 29, toluene below 7,300 parts per billion, and EDB below 0.05. We don't have a lot of fancy biological data on this site, but more just the chemical results. So in terms of implementing it, PetroFix is versatile in that it can be sprayed easily for excavations, it can be injected. I've seen it used for inland spill response. I've seen people use it for tank basin flooding. It's compatible with infrastructure. In this case, contamination was so high, they opted to use excavation here. And then we came in and we sprayed Regenesis into the base of this excavation, which went down to about 13 feet. And that was a primary method for them to try to get rid of a majority of the smear phase in LNAPL that was at the site. But going deeper than that was pretty expensive, and they decided that they were going to backfill that and come in. And we actually did a pretty heavy dose of PetroFix and a lot of electron acceptor blend from 13 to 16 feet below the ground surface. Then we implemented a series of barriers to truncate and stop the movement of the plume going off site, and a little bit of a grid at the far down gradient well. We used a total of 13,600 pounds of PetroFix and 52 points for these barriers and about 1,200 pounds of PetroFix down gradient. The site, by the way, was a sandy site primarily with intermittent layers of a silty sand and clay sand. In terms of results for benzene, we're seeing what we like to see, which is with a carb and a colloidal carbon, you're going to see some fast results that go down. First quarter post application, we see in all the wells on site dropping well below the 29 ppb RBSL or closure limit needed for the site, actually hitting non-detection very low limits. We also see the same for the other BTEX compounds such as toluene. 7,300 was a target, but we're getting all the way down to detection limits for that. And even EDB is doing extremely well. So in conclusion for that, benzene, toluene, EDB hit their limits. LNAPL removal achieved and sustained, I guess, not being observed any further at the site, which was one of the goals. And so we hope to see further results from this come out and to be able to issue that as a site closure report or a case study. So with that, going through it fairly quickly to keep it on time, why don't we transition over to Q&A?
All right, thank you very much, Todd. So yeah, that concludes the formal section of our presentation. And at this point, we'd like to shift into the question and answer portion of the webcast. Thanks to those of you who are staying with us. And if you do have to jump off, just know we will be sending out a link to the recording after the webinar. We will be sending out a brief survey. We really appreciate your feedback, so please take a minute to let us know how we did. All right, so let's circle back to the questions here. This is a question for Rick. Rick, the question is, do you think it is useful to supplement PetroFix with additional electron acceptors?
Yeah, it's a good question. Yes, especially in high flux or high concentration areas, or what we call the stubborn wells or areas that need treatment. It's not going to do any harm to the system, and it's really quite a cost-effective way of enhancing the bile. I strongly recommend it. Injection, of course, is something, as Todd mentioned and myself, you need to think about. But yeah, I would highly recommend it for consideration.
Yeah, to add to that, Rick, and just to the audience, that we certainly have done that with PetroFix on site. We have the standard package. There are times where we'll, add more of the standard package. Sometimes there's clients that want to pull it out. There's times we've actually used gypsum and other things of that nature, but it can get a little tricky. So I would say, I wholeheartedly agree with Rick. There are times where it may be necessary. Give us a shout, give Rick a shout. There are nuances that we would want to walk you through to make sure injection goes okay.
All right, so here's another question here. This one's for Todd. Todd, the question is, can PetroFix be co-applied with Regenox or other oxidants in a single injection event, or are separate applications necessary?
That's a good question. I've made a lot of big case for being able to co-apply the electron acceptors. In the case of oxidants, PetroFix cannot be co-applied with an oxidant. I'm not being the PhD or being able to perfectly describe it, but it is disruptive to the chemistry and they should be avoided. So typically what we do is we do sequential injections or separate grid injections to try to avoid them being co-applied.
Okay, thanks, Todd. So here's another question for Rick. Rick, the question is, have you tried using an oxidant with the PetroFix in high mass plumes?
Yes, actually the case study we just did, but we use it fairly often in areas of high mass or cores of plumes. But as Todd said, we generally do it sequentially. We apply the oxidant first, wait a bit, and then apply the PetroFix in this case.
Okay, here's another question, might apply to both of you. Do you ever have to reapply the electron acceptor?
So I'll start there. Rick, you might actually have an opinion on that as well. It depends. We've had a very few sites on that. Now, there are times where you inject PetroFix and then some wells work great and some wells are not responding as well. And if you go through and you diagnose it, a lot of times it's a delivery challenge. It's not a problem with the amount of carbon or electron acceptor we put in, but sometimes there are other additional mass flux that's coming in, and there have been actual sites where we've just come out and for cost savings measure, knowing that there's a good amount of PetroFix already in the subsurface, there's no need to re-inject it. So we have actually come out at times to do a reapplication, of the package. I would say that that's generally pretty rare, but we do it occasionally.
I would fully agree with Todd. I mean, there are rare occasions when we actually have to come back, but usually it's a distribution issue, as Todd said. And if it's not a distribution, then it's usually the absorption sites on the carbon have been exhausted. So you might probably just need more carbon, but that's rare and it's usually a distribution problem.
All right, thank you both. So here's another question for Rick. Rick, the question is the PetroFix effective on MTBE and TBA?
We do not use it on TBA or MTBE directly. If you have those two, usually you have petroleum hydrocarbons hanging around, BTEX and that too. So we'll use the PetroFix on the hydrocarbons, and then we'll enhance it with something like ORC to go after the MTB, TBA, depending on their concentrations.
I concur. We typically do the same with our designs. Depending on concentration, you often see us, adding oxygen release compound advance, typically in a separate grid, is what we typically do for those types of sites, particularly for TBA.
All right. So here's another question. This one is for Todd. In scenarios where PetroFix is detected in monitoring wells post-injection, how do you sample?
That's a great question, actually. I didn't have time. I wanted to put some additional slides in there, some best practices. But so, the product is made as a colloid to distribute well and then a coat. So it doesn't coat right away. It can be suspended. You want to see that suspension because we end up using the material as a tracer. And so, if you're not seeing PetroFix in your wells, you might want to, particularly if those wells are actually within the injection radius, if you're doing a tight grid in an area, you might want to check what's going on with the injection. But if everything's going well and you're seeing that in the well, that's good news. It usually goes away after a few weeks to a few months, but it is possible to sample. Typically we tell people just to wait, and usually after a quarter or two, everything clarifies down to a level where it's benign on a laboratory sampling technique, which is about 100 milligrams per liter PetroFix. And mind you, that's still very dark. We do have field concentration kits that we ship with every single PetroFix shipment. It's taped to the top. So tell your drillers, if you're sending to a driller, to save those for you, and you can use those to measure that in the field. There are other techniques. We actually do have a groundwater sampling guidance document on our website, which goes through a few techniques, but there are laboratory techniques that you can use. In fact, Rick himself, many years ago, was pivotal in help developing some of these to be able to do almost like a flocculation cleanup technique, or the use of passive diffusion bags could be used if needed, particularly with some clients they inject and they want to sample within 2 weeks or a month. They don't have a couple months to wait or a few months to wait. There are ways to do it.
All right, thank you, Todd. So here's another question for Rick. Rick, the question is, which injection method provided the most effective distribution of the PetroFix?
By far the direct push. It just gives you lots of flexibility on vertical as well as lateral distribution. Screens tend to be more, well screens tend to be more susceptible to heterogeneities, we find in our studies and our applications. So if possible, we always recommend direct push, but sometimes, i.e. in fractured rock or dense tills or dense media, you don't have much choice and have to use in wells. But I would suggest if you do use wells, try to use as small length of screen as possible.
All right, thanks very much, Rick. That is going to be the end of our chat questions. If we did not get to your question, someone will make an effort to follow up with you. For more information about remediation services from InSitu Remediation Services Limited, you can visit irsl.ca. If you'd like to learn more about remediation solutions from Regenesis, please visit regenesis.com. Thanks again very much to our presenters, Rick McGregor and Todd Harrington, and thanks to everyone who could join us. Have a great day.